Hello, my name is Evgeny Shavelzon and I am a PhD student with Dr. Yaniv Edery at Technion, Israel Institute of Technology. I will present you today the results of our joint study with Professor Erwin Zehe from Karlsruhe Institute of Technology titled Linking Subsurface Chemical Weathering and Evolution of Preferential Flowpaths using Nonequilibrium Thermodynamics. So, chemical weathering and emergence of preferential flow paths. Where is the link? Chemical weathering involves interaction between reaction and transport processes, leading to erosion of soil or rock. It plays an important role in geophysical applications such as CO2 sequestration, reactive contaminant transport in soil, and acid injection in petroleum reservoirs. During chemical weathering, the invading fluid induces dissolution precipitation of porous medium, affecting its transport properties and leading to transport reaction interaction. As a result, preferential flow paths emerge in the medium. They dominate transport and act as the main conductive channels in the medium, leading to transport self-organization. The emergence of preferential flow paths is a sign of disequilibrium in the system, as they indicate presence of gradients in pressure and solute concentration distributions in porous medium. Therefore, the emergence of preferential flow paths is subject to analysis within an equilibrium thermodynamic framework. Now, from the non-equilibrium thermodynamics perspective, we consider the medium that undergoes chemical weathering as a non-equilibrium system, subject to inflow of free energy in the form of hydraulic pressure head gradient that maintains flow in the medium, and chemical potential gradient due to inflow of reactive species that maintains reaction. These sources of free energy are responsible for maintaining disequilibrium in the system, as indicated by the presence of gradients in pressure and solute concentration distribution in porous medium, which are characteristic to the emergence of preferential flow paths. Dissipation of free energy occurs via friction, mixing, chemical reaction, and heat transfer. This brings us closer to the key question that we ask in this work, which is how does this dissipative dynamics correlate with the emergence of preferential flow paths that result in transport self-organization in the medium? Methodology. To address the research question, we employ a Darcy scale numerical simulation of chemical weathering of calcite porous matrix due to injection of low pH water, causing reversible dissolution precipitation reaction. The overall reaction of calcite dissolution can be represented by the equation shown here, where calcite reacts with carbonic acid to produce dissolved calcium and hydrogen ions. For simplicity, we assume an abundance of a calcite as well as of a dissolved calcium, making them non-rate limiting. The rate limiting factor in our scenario is the production of carbonate, which is controlled by the available hydrogen ions. Thus, the reaction can be simplified to an interaction between the hydrogen ions H+ and the carbonic acid. So, in case of dissolution, some of the hydrogen ions transform into carbonic acid and vice versa. The direction of reaction is governed by the deviation from chemical equilibrium, defined by the concentration of hydrogen ions and carbonic acid, as shown in the corresponding Bjerrum plot for carbonic acid dissociation. The reaction transport interaction in the porous matrix is simulated in our study using the Lagrangian particle tracking approach, where we apply boundary conditions of hydraulic head gradient between the inlet and the outlet of the computational field, as shown in the plot below, and inject the reactive particles that represent the invading low pH water at the inlet. The ensuing dissolution precipitation reaction alters the transport properties of the medium, leading to redistribution of the flow. Porous matrix is represented by synthetically generated hydraulic conductivity fields of varying conductivity. Following the simulation, we calculate the entropy generation rates of pertinent dissipative processes using non-equilibrium thermodynamics and correlate them with transport self-organization quantified with Shannon entropy, which is a concept from information theory that can be used for to quantify self-organization. Now to results. We analyzed the evolution of chemical weathering of calcite porous matrix by running our simulation on conductivity fields of varying heterogeneity, represented by the variance of conductivity of values of 1, 3, and 5. These are shown in the upper row. We first examine the spatial distribution of the reactants in the field by observing the normalized concentration plots for hydrogen ions, which is shown in the lower row. The correlation between the degree of heterogeneity of the field and the ensuing emergence of preferential flow paths becomes evident as higher heterogeneity corresponds to higher degree of transport self-organization, where the particles are being funneled into a few dominant preferential flow paths while skipping most of the field. The following video presents the dynamics of the spatial distribution of both the hydrogen and the carbonic acid for the mid-heterogeneity case of sigma equals 3 as a function of time. By observing the color range for both species, we see that hydrogen is more channelized while the carbonic acid is distributed more homogeneously. Average hydrogen concentration, shown in bright green, is lower than that of carbonic acid, which has a characteristic yellow coloring. While the hydrogen concentration in preferential flow path is much more pronounced, which is a color of saturated red. We interpret this as a direct influence of preferential flow paths established in the field. Due to constant influx of hydrogen, their significant portion is traveling in preferential flow paths. On the other hand, carbonic acid is introduced into the field only due to dissolution reaction with the porous matrix, that is, more likely to occur away from preferential flow paths, as there are more chances for the chemical equilibrium to be disrupted. Thus, its distribution is more homogeneous. These observations are confirmed by the plots of normalized Shannon entropy of particle distribution versus a dimensionless time, which is the simulation time normalized by pore volume time, for different heterogeneities. Recall that a decrease in Shannon entropy represents an increase in self-organization. We observe that Shannon entropy first increases as particles build up in the field until a tipping point is reached. This point is identified as the time at which preferential flow paths are fully established. After this point, Shannon entropy decreases as particles further self-organize within the established paths. Since the reaction between the preferential flow paths is dominated by dissolution due to constant influx of hydrogen ions, this leads to an autocatalytic process where preferential flow paths become more conductive, thus attracting more of the injected hydrogen ions. We also observe that Shannon entropy is lower for higher variance, sigma values, as a preferential flow paths are more pronounced for those high heterogeneity values. Recall again that a decline in Shannon entropy means an increase in self-organization. Finally, we note that Shannon entropy of hydrogen ions is consistently lower than that of the carbonic acid, thus confirming our observation from the previous slide that hydrogen is more associated with preferential flow paths, thus exhibiting higher self-organization, which again signifies that precipitation occurs more at the periphery of the preferential flow path. and node within this path. And finally, we consider the entropy generation sources that are characteristic for subsurface chemical weathering. These are percolative entropy generation due to frictional dissipation. You can recall an example of a viscous flow in pipe where the pressure drop is balanced by the frictional stresses due to fluid viscosity. Mixing entropy generation due to mixing of different chemical species, and reactive entropy generation due to chemical reaction. We first consider the reactive entropy generation. We calculate the entropy of the useful reactive events that were not cancelled out due to reversibility of reaction and thus have affected the conductivity field and transport of organization. Figure on the left presents the normalized reaction entropy generation as a function of dimensionless time. Entropy increases as species build up in the field until a tipping point is reached. This point is identified as the time at which preferential flow paths are fully established. After this point, reaction becomes more organized in preferential flow paths, leading to a decrease in reaction rate and thus a decrease in reaction entropy, while the rate of decrease is higher for lower values of sigma, or a conductivity variance. This can be explained by the fact that the more homogeneous species concentration associated with lower heterogeneity creates more opportunities for reaction in the field, and therefore higher reaction rate and faster channelization, as opposed to the more heterogeneous scenario where the reactive species advance together within the preferential flow path, allowing for less possibilities to disrupt chemical equilibrium. Similar tendencies are exhibited in the right figure that presents the typical distribution of reactive entropy generation as a function of normalized distance from inlet. We observe that a reactive entropy decreases with this distance, especially for higher heterogeneities, signifying an increase in channelization in the downstream direction, as we saw previously. Next, we consider the mixing entropy generation that represents the loss of the free energy due to mixing of species in the field. Figure on the left presents the normalized mixing entropy generation as a function of dimensionless time. We observe that the normalized mixing entropy increases with the sigma, which can be attributed directly to the intensity of transport channelization in the field, as greater channelization, corresponding to higher sigma values, attenuates the mixing processes in the field, causing the species to move in a more organized way within the established preferential flow path, thus increasing the gradients of chemical potential and concentration in the field. The observed tendencies for the mixing entropy generation support our hypothesis regarding the reaction entropy, showcasing that intensification of transport channelization in preferential flow path inhibits the mixing of the reactants, thus leading to a decline in the overall reaction rate in the field. Figure on the right presents the typical distribution of normalized mixing entropy generation as a function of normalized distance from inlet. The increase in mixing entropy generation downstream indicates an increase in the gradients of chemical potential and concentration with distance from inlet, which again signifies an intensifying channelization in the downstream direction, which correlates well with the special tendencies for reaction entropy. And finally, we analyze the normalized percolative entropy generation, which represents the loss of hydraulic energy of the flow due to frictional dissipation in the field. Figure on the left presents the normalized percolative entropy generation as a function of dimensionless time. We observe that the percolative entropy in the field decreases with sigma as well as with dimensionless time, similarly to reactive and mixing entropies, as the coupled reactive transport process in the field evolves, signifying lower free energy losses due to frictional dissipation effects per unit flow rate as a result of the increasing channelization of transport. Figure on the right presents the typical distribution of normalized percolative entropy generation as a function of normalized distance from inlet. Here, as opposed to the other entropy sources, no clear tendencies spatially are observed, as the percolative entropy generation doesn't exhibit any, except for local statistical fluctuations due to heterogeneity of porous medium. And to summarize our findings, this last slide puts together plots that quantify the transport self-organization, which is equal to the intensity of the preferential flow path phenomenon. For that purpose, we use the Shannon entropy that allows us to quantify this phenomenon. And on the other side, the dissipative dynamics that accompany that transport self-organization. These are expressed by the physical entropy generation from various sources, as discussed before. We observed that a clear correlation can be established between the two, indicating that the emergence of preferential flow paths allows to reduce the free energy dissipation rate and thus represents an energetically preferred state of the system. So this is the take-home message, and it also appears in writing on this final slide. We can also add that this established correlation between the transport self-organization and the dissipative dynamics for chemical weathering can be applied, for instance, for geological dating. Thank you. If you have any questions, you are welcome to write me on the email written below, as well as scan the QR code and read our recent preprint that contains this information. Thank you for listening.